And so welcome, Dr. Tan Nguyen. So he's currently assistant professor at Department of Mathematics at US, and before joining, he was at UCLA postdoc with Stanley Osher. So he got his PhD in machine learning from Rice University. He co-organized a lot of interesting workshops, including deep neural models and differential equations in ICLR, and also he's done internships with Amazon AI and video research, and he has received many awards, including this Computing Innovation Postdoctoral Fellowship, CI Fellows. So today he's going to talk about mitigating over-smoothing in transformers via regularized non-local functionals. So Tan, you may begin.
Yep, thank you so much for the kind introduction, Chen Shao. And it's my pleasure to present my work in the meeting today. And today I will present our recent work on the mitigating oversmoothing in transformer via regularized non-local functionals. Right. So, and this is a joint work with Nguyen, a PhD student at the Rice University, Professor Rich Panak, and myself. All right. So artificial intelligence, right? AI has caused, a lot of revolution in a variety of application recently, including computational biology, pharmaceutical science, material science, and mechanical engineering. And the models underlying the AI is deep learning models, and these models contain of multiple layers, right? For example, in this figure, we have an input data, an input image, and we send to a deep learning model, and the model will process the image from layer to layer, and each layer, the model try to extract a useful presentation of the image. And at the end of the layer, the model will obtain a good set of features that can be used for some downstream task, including classification or linear regression. Right. So in general, a deep learning model will contain two parts. The first part is the feature extraction. For example, in this case, we have a three-layer deep neural network. The input X will be sent to a linear transformation F1, which parameter theta 1, and then a nonlinear activation is applied on the result. And the output of the first layer will be sent to the second layer, and the same processing happens again at the second layer. Right, and at the end of this feature extraction, we obtain a good set of feature. And then that feature, in this case, h of x will be sent to a downstream model for classification or regression. And one particular state-of-the-art deep learning model is a transformer, which is the key model underlying the ChatGPT, right? And transformer has been the backbone of also other state-of-the-art AI model, including PERT, GPT-3, DALL-E 1, DALL-E 2, image change. And the transformer model, back to 3 years ago, we already anticipate, right? Its power, here is the trend at iClear 2020. Right? People see transformer 3 years ago already, have a lot of paper at iClear 2020. It has been used in natural language processing, including neural machine translation, question answering, and textual entailment. Right. Transformer also be used in speech, audio, and visual processing. And of course, I mentioned before, it's been used in AI chatbot, such as in ChatGPT. So like other deep learning model, this transformers model also contain multiple layers of processing. And the input will be processed from layer to layer. The output of the previous layer will be sent as the input of the next layer. If we look into one layer of transformer, we will see two key components. The ring component here is just a neural network. So this is similar to a layer of deep neural network. The key difference between a transformer layer and a deep neural network layer is the red box in this figure, which capture the self-attention, which is called a self-attention. And this red box, what it does is compute the correlation between the input tokens, the implicit token in the input sequence. In particular, right, if our input is a sentence of length n, which means that n word in the input sentence, right? So each word can be approximately a token, right? And the self-attention layer will try to compute the correlation or the similarity between the word in the sentence. So let us look at an example to have a further understanding of what attention does. So here in the example, we have the following sentence. The animal didn't cross the street because it was too tired, right? So each word in this sentence is a token. And what attention does is given a word, is given a token in this sentence, which is it, right? Attention want to compute the similarity between the word it here with all the word in the sentence. Or in other words, it try to capture the influence of other word in the sentence on the particular word it. And it do it for every single word in the sentence. Right. So let's say your input sequence have dimension of n by d, where n is number of words or token in the sentence, and this is the embedding dimension for each word or each token. Right. After attention, you obtain a similarity matrix of size n by n, where the element ij in that n by n matrix will capture the similarity between the token I and the token j in the input sentence. Okay, so mathematically, the self-attention can be computed as follows. Given a input sequence x of dimension n by dx, right? So each token or each word in the input sentence can be represented by x1, x2, xn, right? And what we do is we take in this matrix x and we projected this matrix into three different subspaces via three linear transformation, WQ, WK, and WV, to obtain the new matrices Q, K, and V, where Q stands for the carry matrix, K stands for the key matrix, and V stands for the value matrix. The next step is we compute this QK transpose, right, the matrix product between the carry and the key, and then we normalize the score by a softmax normalization, right? So the softmax QK transpose divided by normalization terms root of D will give you an n by n matrix that capture the similarity between element in the input sequence, and we call that attention matrix. Attention matrix, right? And then we use the attention score to linearly combine the root in the input V, right? In the matrix V. V here is another linear transformation of the original input sentence. And in practice, people also introduce residual connection into transformer, into one layer of attention, followed by a nonlinear mapping, which is in the form of a neural network. So in this figure, this plus side, the residual connection, is this connection here, right? And the F sub L is a linear, is a neural network, usually nonlinear, right? That apply row-wise on the output of the attention. So even though the mathematical formula for attention is very simple, right? The softmax QK transpose multiplied by V. But surprisingly, it works very well in practice. And we currently don't have a lot of understanding of why such a formula give us a very good results on a wide range of tasks, right? So in other words, a good understanding of self-attention mechanism is currently missing. And like in the case of developing new network, when people develop attention and transformer, it's mostly based on intuition and a lot of engineering work to get a working model, right? So a theoretical framework to study attention is currently lacking. And that's the target of our project, right? We want to develop a theoretical framework to study attention. Another problem with the self-attention in practice is known as over-smoothing, right? So deep learning layer, one of the power of deep learning models is when you add more layer into the model, it means when the model gets deeper and deeper, the performance of the model will increase, right? When you have a lot of training data. But unfortunately, for transformer, what people observe is when we add more layer into the transformer, the performance of the model drops, but not increasing, right? And empirically, what we observe is the output from each layer, like at each layer of transformer, right? You look at the output of that, which is a n by d matrix, right? And what happened is the rows in that output matrix become more and more similar to each other when you have more and more layer in the model. And this is not an over-smoothing issue in transformer because the rows of the output become so similar, the token, right? The token in the output becomes so similar. It means it limit the representation capacity of the model, and therefore the performance drops. To empirically validate this hypothesis, right? We have the following experiment. In the left figure here, we consider the task of image classification, and on the x-axis, what is the layer index, right? So this is the transformer with 12 layers. And on the y-axis, we compute the cosine similarity between the tokens, And again, let me remind the audience what the token is. The token can be considered roughly a word in a input sentence. So let's say your input sequence is of size n by d, right? So each token is a 1 by d row in that n by d matrix, right? And then we compute the cosine similarity between the token using the following formula. And we do that at each layer. And what we observe is when the model gets deeper and deeper, mean more layers are added into the model, the cosine similarity between the token increases. Right here, we only focus on the blue curve, right? So let me explain why. The blue curve here is the baseline transformer model, which is called the date, one popular type of vision transformer, which is the transformer used for computer vision task. Right, so this is the baseline transformer without any modification. The orange curve is our model, our own model. Of course, we will show later our model, it will mitigate over smoothing issue. But for now, let's focus on the blue curve only, which is the baseline transformer. When the model gets deeper, the cosine similarity between tokens become larger and larger. It means the token become more and more similar to each other. And we also consider another task, which is the image segmentation, and we observe the same phenomenon, which is the cosine similarity increases when the model gets deeper. But then we say, okay, yes, so the token becomes so similar. But what's wrong with that, right? Why we shouldn't want that? So to confirm, the problem, when you have the token becomes too similar, we also run another experiment. So in this figure, right, the x-axis again, the layer index, right, and on the left here, you have the cosine similarity, and on the right, you have the error rate of the models, So we see that when the cosine similarity increases, which when the token become more similar, then the error rate also increases, right? So which means over smoothing hurt the performance of the model, right? And we want to figure out a way to mitigate the effect so that we can construct a very deep transformer model to obtain better and better performance. And the weapon that we use to tackle down these two problems, first is to construct a mathematical framework for attention in transformer, and second, to mitigate over smoothing. Our weapon is using non-local means denoising. And what we do, we will show that later in my talk, we will show that attention can be derived from the non-local means denoising. And we can modify that non-local mean denoising in order to mitigate the oversmoothing issue. But before we talk about how transformer connect to non-local mean denoising, let us spend a few slides to discuss what is non-local mean denoising, right? Let's say we have a noisy image, like this image on my slide here, right? One of the most popular way that we do denoising, for example, if you want to denoise the image batch here, the image batch B here, so one popular way is we consider the patches that's similar to batch B, right, and take average of the patches in the image, so that we can kind of blur the image a little bit and remove the noise, right? And now the question is how you define a similarity, right? Traditional way, people define the similarity between the image patches by their distance, right? So it means like if a patch in the neighborhood of B, then well, rarely that they are similar to B, right? And that is the Gaussian smoothing, right? You consider the local batch, the batch in the local neighborhood of B, and then take average of the batches, right, to denoise this batch B. But then it might not make sense because, for example, if my batch B is, for example, like in this area, right, like you have an edge there, then probably the budget here and here will be very different, right? The budget here and here will be different, and take the average of them might not make sense, and you will lose the edge information. So instead of that local approach to do denoising, people, in the previous work, right, people propose let's do the non-local approach. And in the non-local approach, they say, okay, the batch that's similar to the given batch B here might not need to be in the neighborhood of B, right? We can consider the whole image, budget in the whole image, and find the one that is most similar to B, and use the budget to denoise B. So in particular, in this case, we see that the batch Q1 and the batch Q2 here are similar to B, right? So we want to put the weight, the influence of Q1 and Q2 on B to be bigger. So the W here will be bigger. And the batch Q3 here, it doesn't look like B at all, right? So we reduce, we make the weight between B and Q3 here smaller. And this way, Q of B and W of B and Q1, W of B and Q2, and W of B and Q3 will be used to compute the weighted average on the budget in the image to denoise the batch P here. And that's known as the non-local mean denoising. It allows us to remove the noise while also reserving, some important information like edges. And mathematically, the non-local mean denoising can be written in this following formula, right? You have the batch IJ, the batch the batch xi that you want to denoise, right? So you consider on all the batch in the image and the neighborhood around the batch, and you can build a distance, right, between those neighborhoods, and use that to denoise the batch that you of your current batch. And here we do a Gaussian kernel to compute distance between the two batches. Right. So in the next part of my talk, what I will do, I will link the non-local mean methods to self-attention. And then we develop a non-local variational denoising framework for self-attention. So before we already talk about the intuition of non-local means and how we use that to denoise images. So let's make it more mathematical gears, right? So let's consider we have a noisy image f sub x. So this noisy image is the observed image, right? We see this image, and we want to reconstruct the clean image u sub x, right, from this noisy image. So f sub x will equal to u sub x plus some noise, right? And we want to remove this noise so that we can reconstruct the clean image u sub x, right? And let's discuss the setting of the denoising problem, right? So we can consider this the clean image U sub x, right, as a function, right? A functional. Sorry. So the U sub x, a function contain like u1x, udx, right? Here d is a number of pixels in the image, and x here, d here stands for the the d here actually stands for the yes, sorry. So the d here, so it's not fun for the number of pixels. So the embedding dimension in the yes. So let me verify this a little bit.
D
so
should be the channel, right? Is it? D is the number of channels.
Not necessary. D can be considered as the embedding fee, the embedding dimension of the signal, right? So x here is the index of the pixel, right? You have like u sub x, which you consider you consider the pixel at the location x, and then in for that pixel you can have a vector representation of that. So in the particular case, like Chen Chao say, right, so it in the specific case it can be a number of channel, right, in RGB, and D here can be a 3-dimension, right? But it in general it can be any embedding dimension. Let the observed intensity function f sub x, right, to be the observed noisy signal at x, and we can write f sub x equal to u sub x plus the noise. So is it clear here about the setting of u and f?
Yeah, I think you can continue if it's not.
Yes. Okay, so let me keep going. And in order to denoise the image, right? So we can consider the rational denoising. We can consider the following optimization problem, right, in which we want to minimize the energy function E between the clean signal and the noisy signal. And the energy function E, it contains two terms, right? The smooth term, the J sub U, and the fidelity term, the G between U and F, right? The smooth term here, we kind of like do the blurring, right? You want in the clean image, you want to invoke the smoothness, right? The path should be look like similar, and the fidelity term G between U and F will allow us to reserve some important information from the noisy image as the edge. And we can represent the smooth term J here in the following way. Right? You just compute the distance between budget and the image, right, weighted by the kernel. And the fidelity term is computed by the L2 norm between the clean image and the noisy image. Right. So I mentioned before, minimizing the regularizer J sub U promote the smoothness of U, and minimizing the convex fidelity term G sub U and F will preserve the relevant information in the noisy image F sub X. Right. So what we will show in the next few slides, it will show that if we just minimizing this J sub U, the smooth term, what we obtain will be the self-attention in the transformer. Right. And then we expand, let us do that. So first we expand the J sub U into the following form, right? And then we take the gradient of the J with respect to U, because we want to find the clean image U, right? So we want to minimize J with respect to U. So we take the gradient of J with respect to U, and we obtain the following formula in equation 4, right? dJ over du J, which is particular du J is like in one embedding dimension in the U. like for example, in the RGB image, like Chen Chao mentioned, right? It can be the U of J is just like a channels, right? Like indexed channel in that particular case. And given this formula, right, we confirm the radiant flow, right? du over dt will be equal to the negative derivative of J with respect to u in the following form. Right. So given the gradient flow, we will solve the gradient flow using the Euler method with the step size that we choose to be this one. And we can write the solution, right, of this ODE in the equation 6, right? The solution of the ODE is given by equation 6, right? Where the big K here is a symmetric kernel. It's the KXY plus the KYX, a symmetric, right? And in this particular case, we choose the initial condition, uy at time 0 to be the v sub y, and you will see the v sub y later to be the vector value in the attention, the value vector in the attention. And now the last step is we will choose this kernel K, this kernel big K, right? So how we choose the kernel big K. So in image denoising, right, we can choose big K to be a Gaussian kernel. But because we are in the deep learning area, right, era, right? So we can say, okay, how about we try to learn how to learn this kernel matrix, and we can write this kernel kxy in the form of exponential of kx transpose ky, and then we divide it by some normalization terms with d. It is again the embedding dimension, right? Here, this k here will correspond to the key vectors in attention, and it is learnable. So we train the model to learn this kernel, and then you can write the whole thing in terms of equation 7, which turned out to be a symmetric self-attention. It's symmetric because we don't have a carry yet. It's just the ki transpose multiplied by kj, where k is the vector, is the key vectors in the self-attention. And we can obtain, like given this symmetric attention, right? We can obtain the attention toward you in practice by breaking the symmetry. We can replace the k sub I by the q sub I, which is the carry, right? And both q sub I, both the carry and the key, right? The q and the k here are projection of the input, and by replace k sub I by q sub I, we allow the model, right, to be more flexible, right? It will learn this the carry and the key at the same time. And we summarize our results in this following theorem, right? So we are starting from a rational non-local image denoising, right? We can derive this self-attention in transformer by minimizing the smooth term, right, in the non-local denoising. And just with the result, we already have a sense of why over-smoothing happens, right? Because what attention does, it tries to minimize the smooth term, whether promote the smoothness in the output. And it means if we repeat that process in multiple steps, equivalently, multiple layer in the transformer, the image will finally become a blur image, and and a blur image. And it will, it will equivalent to the oversmoothing issue when the token in the output to be the same. So it's an intuition of, why self-attention will result in oversmoothing phenomenon. But let us try to prove it mathematically, right? So we employ the random walk analysis of oversmoothing to prove its result. Right, so from the reference flow of U, right, we can write this the ut sub I in the following form in the equation 8, right, where A here can be either a symmetric attention or non-symmetric attention. And then we construct a random walk on the vector values of attention, and this random walk B sub bt sub the random walk B sub t here, define a follow. Right, B0 I equal to V sub I, and the transition probability will be given by the attention score Aij. And then we prove the following lemma. that we let U and B define isable, right? Then we have the UTI equal to the expectation of the BTI, which mean the output of the self-attention, to be the expected value of a random walk, defined on the node on the token of the of your input sentence. And then we have the following theorem. When we know that the output of the self-attention will be the expected value of the random walk, we will show that the random walk b sub t, the expectation of b sub t when t go to infinity, will also convert to a constant. That show that the output of a self-attention also converges to a constant, and that's called the over-smoothing. So now we develop a mathematical framework for self-attention, and we use that framework to give intuition of why over-smoothing happened, and then we have a proof for the over-smoothing in self-attention in transformers, right? So now let us discuss how we can mitigate this over-smoothing problem, right? So what happened is, in order to the self-attention is derived by minimizing the smooth term in the non-local denoising framework. But if we revisit my previous slide, right? In non-local image denoising, in addition to the smooth term, we also have the fidelity term. And the fidelity term try to preserve the important information in the noisy image, such as the high frequency information in a noisy image, like edges, for example. So one simple way that we can mitigate the over-smoothing problem in transformer is we try to minimize both the smooth term and the fidelity term at the same time, right? So we add back the fidelity term into our energy function. And then using the similar approach, we can develop a new attention, which we call the NeuTRENO attention, right? So this NeuTRENO attention will correspond to the right flow of minimizing the energy function with both the smooth term and the convex fidelity term. And compared to the baseline attention, this NeuTRENO attention only involves a simple modification, which is we add a residual information, a small residual information into back into the attention, right? Where here the V0i is a vector value at the very first layer in the transformer, and Vi here are the current value vector at each layer. And with that, we define the NeuTRENO. The NeuTRENO transformer is a transformer that uses our NeuTRENO attention, and it has ability to overcome the over-smoothing problem. And we have a theory in our paper to prove that when you add back these the fidelity term, the convex fidelity term into the energy function and derive the dynamic in equation 10 here, then the output, the evolution of the U sub x, the output of tension under this dynamic, does not convert to a constant vector. And that helps showing NeuTRENO mitigate over-smoothing issue, right? And here we saw a figure that try to illustrate our NeuTRENO transformer. So at the very first layer, right, we store the V0, right, the vector, the value vector at the first layer of a transformer, right? And then in each subsequent layer, we take the value vector V1, for example, the first layer, you take V1 and you subtract V0 from Z1 and you scale it by the scale factor alpha and add it back to the output of the attention. And we do so at each layer. So very simple modification. Will not increase memory, will not slow down the processing, but it obtains better performance by mitigating the over-smoothing issue in transformer. And to confirm the advantage of our proposed NeuTRENO transformer, we run a variety of experiments, right, to justify the benefit of our methods. So here in this in our work, we consider image net classification, image segmentation, and also a language modeling task on Wikitext 103. In particular, let's look at the image net classification, right? So let's look at these three lines, right? The submark date is a baseline vision transformer without any modification. And then the NeuTRENO date is we replace the submark attention in that transformer by a NeuTRENO attention. And then we train the whole thing end to end, right? And we see that when we do that, we obtain a better performance than the baseline. The improvement here is almost 1%, which is significant for ImageNet. And then in the last one, NeuTRENO adaptation, what we do is we take the submark date, we train it. So we have a pre-trained submark date, and then we take that pre-trained model, we replace the submark attention by the NeuTRENO, and then we fine-tune for a couple iteration. And we also observe that when we do so, our NeuTRENO, when we train from a pre-trained baseline model, also obtain a better accuracy than the baseline. In this two line, right, we try to solve it. We combine our NeuTRENO with a state-of-the-art method to mitigate oversmoothing with a fit scale. Then we also improve the state-of-the-art methods. And a similar result for image segmentation and language modeling. Right. So another experiment that we do is we want to confirm that in transformer, right, from layer to layer, right, it will try to minimize the smooth term trace of U, right? Because in our theoretical result, we saw that when we try to minimize the trace of U, we obtain the formula for the attention. And now we empirically validate that, right? So here on the x-axis is the index, and on the y-axis is the trace of U, right? So both during the train and test, we see when we add more layer in the transformer, the trace of U, the smooth term, will be decreased. So it's so that by the empirical result, we justify that transformer, actually the baseline transformer, actually try to minimize the trace of U over layer. And finally, we want to show that our methods, NeuTRENO, will help mitigate oversmoothing, right? So we discussed the blue curve already at the beginning of my talk, right? When we add more layer into the model, the cosine similarity between the token will be increased, right? This is for the baseline date, the vision transformer. For our methods, the NeuTRENO date, which is the orange curve here, right? We see like one number of layer, when we have more layer, right, the cosine symmetry is still small, even though at the end it still slightly increase, but it's it's still much smaller compared to the baseline. And this holds for both the trend model and the randomly initialized model. And the results show that our NeuTRENO reduce oversmoothing in image in both image processing and natural language processing tasks. So in conclusion, in this work, we develop a non-local rational denoising framework for self-attention, right? And then we set line on oversmoothing issue that limit the representation capacity of transformer. And then using our framework, we develop a NeuTRENO, right? A new class of transformer that are able to alleviate the oversmoothing issue. And then we provide theoretical proof for our results. And with that, I will end my talk and open the floor for questions from the audience.